Alright, Assalamu alaikum. So a quick summary of what we've been doing so far with atomic and molecular systems. For the helium atom, we first considered the helium atom, an isolated helium atom with 2 electrons in it. And we found out, we solved the helium atom, and we found out that the ground state is a singlet state, right? 1s naught. This corresponds to the state, the spatial state 1, 0, 0 crossed with 1, 0, 0, and this must combine with the singlet state alpha, beta, beta, alpha. So if there are 2 electrons inside the ground state, they must be antiparallel. They must be the singlet state. And we derived the energy for the singlet state. Okay? So the energy had a 0th order term, and on top of it we had a perturbation, which was due to the interaction between the electrons. Then we also found out the excited state, the first excited state, and we found out this interesting effect, that is the states split up. So this manifold corresponds to the state in which one electron is in the 1s state and the other electron is in the 2s state. Right? Which means that we have, and this manifold represents one electron being in the state 1s and the other electron being in the state 2p. And we computed the energies of these states. And we found out that with respect to a 0th order energy, there is a Coulombic term I, and on top of this, there is a splitting between these states of some magnitude, say 2J1. Alright. Likewise, there is some Coulombic energy I dash associated with this energy, and on top of this there rides a splitting 2J2. And we notice that this manifold is being split with an integral, which is the exchange integral, and this manifold is being split. And this is a triplet state, whereas this is a singlet state. So this is S3 multiplicity 3, this is S multiplicity 1, this is a singlet, this is a triplet. And for this state, since the spin is 1, L is 0, we have J equals 1. For this particular configuration, S is 0, L is also 0, so J is 0. So these are the term symbols. Now this splitting of the singlet and the triplet manifolds is a result of the exchange degeneracy. Okay, this is something that we learned about the helium atom. Likewise, for this manifold, that is one electron is in the 1s state, the other electron is in the 2p state. Both of these states have an angular momentum 1, total angular momentum 1, so these are capital P term symbols. This is a triplet. So this is 3 over here, this is a singlet, this is 1 over here. Now J, capital J, since S is 1, L is 1, so J can take up 3 terms, 3 possibilities, 0, 1 and 2. Whereas for this case, S is 0, L is 1, so J can only take up 1 value. So these are the term symbols for all 5 of these states. This is the ground state, and this is the first excited manifold. And within each of these states there is a splitting. which is a result of the exchange interaction. This is something we've learned about the helium atom. By the way, these excited states are given in the general form as following: 1, 0, 0 crossed with 2 L M L plus minus 2 L M L crossed with 1, 0, 0 with the appropriate singlet or the triplet state. Okay? Combined with the appropriate spin state, right? You have to combine them properly to satisfy the symmetrization postulate. Now this exchange integral J, we all know, we've derived this. This is given by 1, 0, 0 crossed with 2 L M L 1 over E square over 4 pi epsilon naught R2 minus R1 2 LML crossed with 1, 0, 0. So this is our J. For this manifold, I just put in L equals 0 here. For this manifold, I put this L equals 1 in here. So this is the exchange integral. No classical description, it's a purely quantum mechanical integral. It's quantum mechanics at its best over here. Okay? So you cannot say that this is a Coulombic interaction, because the first electron is, there's a transition of the first, transition element of the first electron being connected through this Hamiltonian to the first electron being in another state. So this has no classical description. That's why it's hard for me to describe what this really is. It's a transition matrix element between two different states. Now this coupling over here is called the exchange interaction. And this is what we've learned about the helium atom so far. Alright? Now we also learned that if we zoom in onto this manifold, for example, we have some zeroth order energy. On top of this we have a Coulombic term, I, and disposed about these I, this I level are the singlet and the triplet states, and the triplet is lower in energy. So to the right of this dashed line, I've drawn the triplet states, and to the left I've drawn the singlet states. This kind of representing atomic levels, electronic levels, is called a Grotrian diagram. And you would like to separate out the singlet manifold from the triplet manifold. Okay? Because transitions, optical transitions between the singlets and the triplets are not allowed. This is what you learn in atomic physics. Okay? So there's no possibility that a transition from this first excited state to this state can take place, because this is the inter-singlet triplet intercrossing. This is not allowed. The probability for this happening is really low. Therefore, if you have electrons excited into this state, this is going to be a metastable state. It's going to have a high lifetime. Okay? So this is the singlet manifold, this is the triplet manifold. Alright? If somehow you can have a molecule in which only the singlet states are populated, then you have what is called an a para molecule, for example, para-helium. If you have some possibility of only having these triplets populated, it's called an ortho molecule. You can have para-helium, ortho-helium. It's easy to make para-hydrogen and ortho-hydrogen. You have para-fluorine, ortho-fluorine, etc. So all of these, by the way, are diatomic molecules. Anyway, we've seen that this particular state is has an energy I minus j. This particular state has an energy I plus j, where j is given by this exchange integral. This is something we've calculated. And by the way, we're looking at, this is the 0th order energy of the first excited state. This is not minus electron volt, 6 electron volt. We've calculated this energy, and it's given by the Rydberg constants, and these are the splittings, the exchange splitting. Alright. And if j is positive, then this term is smaller than this term, and the triplet energy is less than the singlet energy. So the triplets are the ground state, which means that parallel alignment of the spins is preferred, which also means that ferromagnetic alignment is preferred of the electrons. Then we studied the hydrogen molecule. First we studied the hydrogen molecular ion, and then we looked at the hydrogen molecule. For the hydrogen molecule, we noticed that the ground state is the singlet state, and there is a splitting between the singlet and the triplet state. The singlet state, in which the two electrons have a spin that is antiparallel, that's the ground state. And we computed this energy splitting, as once again we computed it in a similar fashion. So these are the triplet states. It's threefold degenerate, and this is the singlet state. We did a complete calculation under the Heitler-London approximation to this. Okay. Now this energy separation turned out to be the following. The energy for the triplet was given by 2E1 plus x over 1 plus s minus some j dash 1 plus s. Okay, this is something we will calculate in class. Likewise, the energy for the singlet state is given by 2E1 plus x over 1 minus s plus j dash over 1 minus s. E1 is 13.6 electron volt, the ground state energy. X represents the Coulombic integral. Okay, I don't want to write this down again. It represents the Coulombic integral, and J represents an exchange integral. Okay? So what I would just like to do, so this is a Coulombic term, Coulombic. And this is an exchange term. And this S is the square of the overlap integral. It's a double overlap integral. Okay, I would just like to write down this term J dash. J dash is given by this overlap integral. 1 R1, where 1 is an atomic orbital, 2 R2, which means that the second electron is associated with the nucleus B, E square, or not E square but H prime. H prime are all the Hamiltonian terms which involve interaction between the electrons and the other nuclei. So these are all the terms in the Hamiltonian besides the pure atomic Hamiltonians. 1 R2, sorry, 2 R2 crossed with 1 R1. 2 R1 crossed with 1 R2. Okay. Alright, so this term represents electron number 1 associated with nucleus 1, electron number 2 with coordinates R2 associated with nucleus B. This represents electron number 1 with coordinates R1 associated with nucleus 2, and so on. Electron number 2 is associated with nucleus number 1. So this is the J prime exchange integral. Now if you look here, you have a Coulombic term and you have an exchange term, and if you subtract these terms, you will get the energy separation between the singlet and the triplet states. Okay? Now the singlet is lower in energy. For hydrogen molecules, this term turns out to be negative. When this term turns out to be negative, the singlet is lower in energy. So, antiferromagnetic alignment is preferred. The singlet is lower in energy. Here, the triplets are lower in energy. J is positive. Here, this J is negative. And the singlets are lower in energy. Now, all of this could be neatly modeled through the exchange Hamiltonian. This is something we've already given a hint about. So the exchange Hamiltonian, we've argued, is motivated in the following fashion. Remember, it's a toy Hamiltonian. I've already talked about it. The Hamiltonian, say for the hydrogen molecule, has a part that only depends upon the atomic Hamiltonian. There's just two isolated hydrogen atoms. So this will be the combination of H atom 1 and H atom 2. Okay. And the eigenvalues for H naught will be 2 times E1, because there are 2 electrons. There are 2 independent hydrogen atoms inside the molecule. Plus there are Coulombic terms. Okay? Plus what the Heisenberg model suggests is that what you would like to do is you would like to include a Coulombic term whose eigenvalues are simply corresponding to the Coulombic energies. So the eigenvalues correspond to these energies. So there is a Coulombic part, and on top of this Coulombic part, there is an exchange integral, Hj. Okay. Remember, when we originally wrote down the Hamiltonian did not include any spin parts. So what Heisenberg's model in the 1920s proposed is, alright, the Hamiltonian doesn't include a spin part. However, we observe that different spin configurations have different energies. So the singlet has a different energy from the triplet energy. So why not include a spin-dependent Hamiltonian into our model? So this was the proposal, this was the model. And the expectation was that this Hamiltonian will now have a part that only depends upon the spatial coordinates and a part that only depends upon the spin coordinates. Why does, even though the original atomic Hamiltonian doesn't include the spin term, why do different spins have different energies? Because of the symmetrization postulate. Because the symmetry of the spatial wave function dictates what spin state should exist. Because there is a strong correlation, there is a quantum correlation between the spin and the spatial degrees of freedom, which is encapsulated by the symmetrization postulate. Now Heisenberg, by brute force, included a spin-dependent Hamiltonian. And the proposal was that if you solve this Hamiltonian, you will get eigenenergies, you will get the energies of the system. So there will be this part which will give you all the terms which are classically describable, for example, this energy or this energy, the Coulombic energy. And the spin-dependent splitting, which are these terms, will be describable by the Heisenberg Hamiltonian, the exchange Hamiltonian. And this Hamiltonian is given by, it was proposed that it's given by K S1 dotted with S2. Okay, and we found out the eigenvalues for the system. We determined the eigenvalues. So when we solved this system, we found out that the singlet state had energy minus 3a h bar square by 4, and the triplet state had an energy plus a h bar square by 4. So this is triplet, this is singlet. Okay, so we solved this Hamiltonian, we found out the eigenstates for this. Okay, for two spin half particles. Now, what this tells us is that the singlet is lower in energy than the triplet, and the energy splitting is 1 बटा 4 मंकी 3 बटा 4 कितना बनेगा 1. So a h bar square. So the energy splitting is proportional to a. However, a could be positive or negative. So if a is positive, then the singlet is lower in energy, and if a is negative, then the singlet is higher in energy. Okay. Now if you look at the helium atom, the separation between these levels is 2J. So the separation here is A, proportional to A. Separation over there is 2J. So why not put A equals plus minus 2J? So if you put A equals plus or minus 2J, then this Hamiltonian will recover the splitting in the helium atom between the singlet and the triplet states. Hence, the convention is that the Heisenberg's Hamiltonian the exchange Hamiltonian is given by minus 2J S1 dotted with S2. Okay, this is the Heisenberg's exchange Hamiltonian, or Heisenberg's Hamiltonian, or the exchange Hamiltonian. So if J is positive, then the singlet is, if J is positive, S1 dot with S2, for this state, the singlet has the lower energy. Alright? But if J is positive, then the singlet has the higher energy because of this negative sign over here. Remember that this, for the singlet state, let me write this down explicitly. For the singlet state, the expectation value of S1 dotted with S2 is minus 3 over 4 h bar square. Okay, so this is a negative number. For the triplet state, the expectation value of S1 dotted with the S2 is going to be plus h bar square over 4. So now you have a minus sign over here, which means that if J is positive, then the singlet will have the higher energy. Okay? And this will be the triplet state. So this will be the triplet state, and this will be the singlet state. And the energy separation once again is going to be 2J. Now what is the precise overlap integral? This depends upon the system we're talking about. I've written it precisely for the hydrogen molecule, and I've written it precisely for the helium atom. Okay? If the triplet state is the ground state, the triplet state has the configuration alpha alpha or beta beta or alpha beta plus beta alpha. This is called ferromagnetic element. The spins are generally parallel. Okay? And remember that if this is the triplet spin state, it dictates what this spatial part should be. That should be antisymmetric. Alright. So now by brute force, a spin dependent Hamiltonian has been plugged into the Hamiltonian, which reproduces the same result as the Hamiltonian that's calculated from ab initio methods, from direct methods, from first principles. But remember that only for a few simple examples such as the hydrogen atom or the helium atom and the hydrogen nucleus or the hydrogen molecule could direct methods work, ab initio methods work. So in most cases you actually have to apply the toy modulus. Okay? So what we are seeing here is that the toy model reproduces the same effect as the Hamiltonian that we've written from direct principles, from ab initio techniques. Okay, and we can only use these ab initio techniques for simple systems, dihydrogen or helium atom. Likewise, if J is negative, then what's going to happen is that this thing becomes positive. This thing becomes positive. The singlet is then the lower energy state, and anti-ferromagnetic alignment is preferred. So for J negative, we have anti-ferromagnetic alignment. Singlet is now lower in energy. So depending upon the sign of J, you can have ferromagnetic ordering or anti-ferromagnetic ordering. And by the way, ferromagnetic ordering is not the norm, it's the exception. Generally the norm is anti-ferromagnetic ordering. Okay? So now with this toy Hamiltonian we can work wonders, and we can apply this Hamiltonian to real systems. So in this course what I am trying to do is, first of all I am giving you an overview of effects, that is phenomena. I have talked about what happens to a dipole when it's placed inside a field, what the force, the energy and the torque on the dipole. Now I am talking about, then I talked about the dipole interactions without any reference to any material or device. Then I have been talking about the exchange interaction. Then I will talk about the spin orbit interaction. And after I build up these effects, I'll talk about real materials, real devices, real solids. Okay. So now we have this Heisenberg exchange Hamiltonian, and this reproduces the exact results for the helium atom and for the hydrogen nucleus, the hydrogen molecule. We're going to prove it that it does for the hydrogen molecule as well. But we've actually seen that this has a direct correspondence with the helium atom. So if you have, say, a large number of spins, say in a solid, and there are neighbor-to-neighbor interactions, or there are interactions between two nuclei, and all the interactions are pairwise, then the exchange Hamiltonian for this system can be modeled as minus 2 times Jij. Jij, remember, is an exchange integral. It's an overlap integral that has to be calculated. Jij, the spin of the ith spin dotted with the jth spin, summed over all pairs, that is I is less than j. Okay? I is less than j, which means that I cannot be equal to j, because then you're double counting. Okay, so I is not equal to j, otherwise you'll be double counting, or you'll have to do the 1/2 correction if you're doing it in that fashion. So these are all, remember, these are two body interactions, and there could be many of them. So in real systems we have exchange interaction, and in the second homework problem I'm going to give you a problem in which I will ask you that you have two nuclei or two moments that are close together. The energy by which they will interact to the dipolar interaction is going to be really small. The exchange interaction, on the other hand, is going to be really strong. So it's the exchange interaction that describes most of the ferromagnetic and antiferromagnetic behavior in solids. And there could be different kinds of variants or flavors of exchange interaction. We could have spins. If I draw cartoons for spins, we could have spins in which the electron clouds are overlapping with one another. So this is just a rough representation of an electron cloud, orbitals. And there is overlap between the orbitals. Remember that if there is no overlap, then this term is going to disappear. J is going to be 0. So there has to be some kind of overlap. So one possibility is that the spins that we're talking about, the electron clouds, are directly overlapping with one another. The ions or spins are close together. They're in close proximity with one another. Remember, the effect originates from electronic interactions. Okay, not really from spin interactions. Spin interaction just sneaks in because of the symmetrization postulate. So this kind of exchange is called direct exchange. And this is very hard to find in real materials because the exchange interaction, since it involves an overlap, it decays very fast. So it's really a short range effect. So what we could also have are spins or magnetic moments. They're not directly overlapping, but in between we have some non-magnetic ions, such as oxygen. This is an oxygen ion. And the exchange interaction is mediated through these non-magnetic ions. This is, for example, why you see magnetism in iron oxide or the oxides, manganese oxide. This kind of exchange interaction, which is mediated through non-magnetic entities, which do not have a magnetic dipole moment. This kind of interaction is called a superexchange interaction. And we'll learn more about these when we look at practical examples of materials. We could also have the following possibility, is that we have non-directly interacting magnetic species. And they are inside a metal. And we have these itinerant electrons, these free electrons, these sea of electrons that are mobile. And all of these are actually spins, these are magnetic moments. And the exchange interaction is mediated through these itinerant electrons, through these mobile electrons. These are itinerant electrons, itinerant spins. Itinerant from itinerary. So this kind of exchange interaction is called the indirect exchange. So there are different variants of the exchange interaction. You could also have spins in which the magnetic moments are confined to lie in a plane, in the xy plane. Remember that S1 dotted with S2 is a dot product between two vector operators. So it really means S1x, S2x plus S1y, S2y plus S1z, S2z. And from your knowledge of angular momentum in quantum mechanics, you know that if these are spin half particles, then each one of these is proportional to the Pauli operator. So Si alpha is sigma I alpha over 2. So these are the Pauli operators, right? You can never escape quantum mechanics. It's always there. So now if you have your spins, which are confined to have the spin moments lying in a plane, in the xy plane, then the exchange interaction for this 2D spin system becomes minus 2 J S1x S2x plus S1y, S2y. There are no z components because the spins are now confined to lie in the x, the spin moments are confined to lie in the xy plane. Okay. So this is also the exchange interaction. You could also have a situation in which the spins just point in one direction, okay, in say the z direction. For such a case, this Heisenberg interaction can also be defined S1z, S2z, okay. In this case, the exchange interaction is called the Ising interaction. Okay, so you have different kinds of exchange interactions. Now let's do an example. Suppose I have three spins and they are arranged in an equilateral triangle. And the coupling between each pair is identical, J. J is sometimes also called the coupling. Now what I would like to do, the Hamiltonian for this system. Suppose each one of these particles has spin 1. Each one of these particles is a boson. Spin 1. Some nucleus that has spin 1. The Hamiltonian for the system is of course given by minus 2j. Now I split this interaction into pairs. I have S1 dotted with S2 plus S1 dotted with S3 plus S2 dotted with S3. Where my label for the spins is anything. This is 1, 2, 3. And all three of them are spin 1 particles. Now, for a simple exchange Hamiltonian of the form that I've written over here, the eigenenergies are plus j and minus j. The singlet will have an energy given by the eigenvalues. The singlet will have an energy given by plus 3 over 2 jh squared. Okay, so this thing multiplied by minus 2j. The splitting is going to be 2j. So we can find out the energies of the singlets and the triplets. So, which really means that we insert this value for the singlet in here, multiply with minus 2j, we get the energy of the singlet state. We insert this value, multiply it with minus 2j, and we get the energy of the triplet state. Okay? So now what we would like to do, we would like to find out how many possible states exist. You see, you have in this 2 spin half example, you have one singlet and 3 kinds of triplets. Whenever you have a triplet, for example, this triplet, or this triplet, this is a combination of many different states because there are 3 kinds of triplets, and you can lift the degeneracy of these triplets as well. So if I apply a magnetic field to this state, it will split up into how many parts? 1, 4, 5 into 10 parts. This will split up into 3 parts. This will split up into 9 parts. So this triplet will split up into 3 levels. Okay. This 1 will split up into 3, 2 will split up into 5, 0 will split up into 1 level, right? It's just going to be 1 level. So by applying a magnetic field through the Zeeman interaction, these levels are further split up. And the other way of lifting this degeneracy is to the spin-orbit interaction, which we'll learn about. In fact, that's why you see fine structure in your spectra. Okay, these are fine structure effects. You must have learned about this in atomic physics. My task is not to teach you atomic physics. Anyway, for this particular configuration, I would like to find out the energies of the system, and I would also like to find out how many states do I get. So how do I solve this problem? So I know that the total spin, right, or ST square is given by S1 plus S2 plus S3 square, right? And I am interested in calculating these pairwise terms, the expectation values of these pairwise terms in their eigenstates. That's what I am interested in calculating. So from here I can tell that ST squared is S1 squared plus S2 squared plus S3 squared plus 2 times S1 dotted with S2 plus S1 dotted with S3 plus S2 dotted with S3. Right? So this thing is proportional to my Hamiltonian. So I will have S1 dotted with S2 plus S1 dotted with S3 plus S2 dotted with S3 equals S total squared minus S1 squared plus S2 squared plus S3 squared over 2. Okay, so I have to compute the expectation value of this, right, in order to find out the eigenenergies, and then I will know what the eigenenergies of the Hamiltonian are. So now ST, what's the total spin of this system? So these are spin 1 particles. So if you have 2 spin half particles, what is the total spin? 0 and 1. This is how you add angular momentum. Now you have 3 spins. What are the possibilities for the total spin quantum number? What could S be? The quantum number S be? Remember, I am being rigorous here. I am putting hats on top of operators. So without a hat, it means a quantum number. So what is this? What are the possibilities for capital S? At spin 1 just particles here. पहले 2 को ऐड करते हैं, 2 को ऐड करेंगे, what do you get? I get 2, 1 and 0, 0, 1, 2. So for two spins I have possibility 0, 1, 2. Now I add the spin quantum number of this to this. I can get 0, 1, 2, 3. So S takes up 4 possibilities: 0, 1, 2, 3. So the total spin quantum number could take up these 4 possibilities, and the spin state is going to be defined by an S, by total spin quantum number and some ms, the azimuthal component of the total spin. So S takes up these 4 possibilities. Now S1 squared, what's the expectation value of S1 squared? S1 is just 1. So 1 into 1 plus 1, 1 into 2, 2 h bar squared. Okay? So this can take up a value 2, this can take up a value 2, this can only take up a value 2. So now let's, for S capital 3, S equals 3, the expectation value of this term over here, this thing over here is going to be given by h bar square over 2. Now s is 3, so instead of this I write 3 into 4, which is 12, because the eigenvalues of s square are s into s plus 1 h bar square. 12 minus 6, so this is 3 h bar square. 3 h bar square. For s equals 2, for s equals 2, the expectation value of the same term is h bar square 2. 2 into 3, which is 6, minus 6 is 0. For s equals 3, for s equals 1, the expectation value is h bar square over 2 minus 6. 2 minus 6 क्या होता है? Minus 4, minus 2 h bar square. And for s equals 0, the expectation value is h bar square minus 3 h bar square. So the eigenenergies are, you have to multiply all of this with minus 2j. So the eigenenergies are minus 6j h bar square 0, 4j h bar square and 6j h bar square. So you get 4 levels. Okay, you get 4 levels. Zero, J, jar, 0. You get 4 levels. This level has s equals 3, this level has s equals 2, this level s equals 1, this level s equals 0. Okay? And the energies are given by minus 6j h bar square 0, 4j h bar square and 6j h bar square. So there is splitting between these levels. This is the exchange interaction at work. The exchange interaction between these spins lifts the degeneracy and you get different spin configurations of the system with different energies. And if the temperature is not high enough, it's preferentially the ground state that will be formed. It depends upon the number of electrons. Now, if you apply a magnetic field to this system, this will split up into 7 levels. This will split up into 5 levels, 3 levels, and this will not split up. Or through the exchange interaction, you can have splitting. Oh, sorry, the spin orbit interaction. So the eigenstates for this system, for this equilateral system, each spin being a spin 1 system, is given here. Now it's difficult to define what is a singlet and a triplet for these 3 spins. First of all, it's not a spin half system, it's a spin 1 system. So it's not really possible to define what a singlet is and what a triplet is. Okay? So, and whatever the spin is, depending upon the symmetry of the spin state, one has to dictate this will correspond to different spatial states. If these are atoms or electronic systems, each carrying a spin 1. Okay? So this is an example in which we employed the Heisenberg model to come up with a system, a realistic system, G.
So can you model a real system based if the real system that corresponds to the same?
Right, you can always build systems or engineer systems that have 3 spins located on an equilateral triangle. In a ferromagnet, you have a crystalline structure. You can have a honeycomb structure. You can have different kinds of structures in which a particular topology of spins is available to you. Okay. Now let's use the Heisenberg model to calculate the energies, these energies, inside the hydrogen molecule. Okay, and this is probably the last time we're going to see an isolated molecule in this course, because then we have to move on to solids, real systems. This is also real. So, how do I start this discussion? The Hamiltonian, so what we're going to do is we're going to apply Heisenberg's model to the dihydrogen molecule. So we know that the Hamiltonian is given by some H naught plus a Coulombic term, okay, plus the exchange term. This has eigenvalues 2e1, this has eigenvalues corresponding to the Coulombic terms, and this is the exchange Hamiltonian over here. Alright, now what we would like to do is we would like to write a set of basis states, and we like to diagonalize the Hamiltonian in that particular set. Now luckily we've seen that the bonding molecular orbitals are actually eigenstates of this Hamiltonian, right? This is what we've seen. These are linear combination of atomic orbitals. These are eigenstates of this. Remember, there was a Hamiltonian, we diagonalized it and found out the eigenstates for this. So let's use the same bonding molecular orbitals and find out the and express this Hamiltonian in the basis of those bonding molecular orbitals. Okay. Now what I'm going to use a shorthand notation. I'm going to express this this phi b R1 state, which is a linear combination of 1 and 2 by R, just by R. I'm going to do shorthand notation, and I'm going to express the bonding molecular orbital state defined for the second position vector by R prime. Okay. So my basis states are I'm choosing a basis. I'm choosing R dash R dash R as my basis states. In space. Now the spin Hamiltonian, the exchange Hamiltonian only has spin terms. Remember that. Okay? It only has spin terms. So I don't care about the spatial basis states for Hj. I need to define a set of basis states in the spin manifold. Right? So what I do is I define the states alpha alpha, beta beta, alpha beta, and beta alpha as my basis states in the spin space. spin space. Now what I would like to do, I would like to write down Hj in this basis. Now these basis states correspond to these spatial basis states, and they have to be connected properly so that the overall symmetry of the quantum state is preserved. It has to be odd. So these are the spatial basis states and these are the spin basis states. For diagonalizing the Hamiltonian, the Heisenberg Hamiltonian, these states don't matter because this is a purely spin based Hamiltonian. This is just minus 2j s1 dot with s2. Now what I need to do is, let me turn this on so that we can save some time. What I would like to do, I would like to write this Hamiltonian in this basis. So it's a 4 by 4 matrix. So I have to order my rows and columns. So I order them in this fashion. This is alpha alpha, this is beta beta, this is alpha beta, this is beta alpha, this is alpha alpha, alpha beta, beta alpha, beta beta. Now I have to express this term into this matrix, which means I have to compute S1 dotted with S2, say ij, I dash, j dash, where I dash are alpha beta. So these matrix elements I have to compute and put them in here. This is what I need to do. Okay, I need to express this Hamiltonian in terms of the spin basis states. Now I can do that conveniently if I use Mathematica or I use a software, and I would like to show you how to do that. So what I've done, I've defined a tensor product, okay, O cross. I've already defined it. Let me initialize this. So I've defined a tensor product by O cross. Okay, this is my definition of a tensor product. Now what I do is the following. I need to define alpha and I need to define beta. Now alpha I call A in Mathematica, and I define this alpha and beta are orthogonal states. So I define alpha by 1 0, a column vector 1 0. Okay, I can put this in matrix form. This is a column. Okay, it's 1 0. This is alpha. Likewise, my beta can be defined 0 1. It's the orthogonal vector. Okay. Now I need to define alpha alpha, alpha beta, beta alpha, and so on. So my alpha beta, I call it AB, is the tensor product of A with B And if you want to look at this, this is, sorry. Likewise, I can define AA, alpha alpha. Okay. I can define beta alpha. Now the ordering is important, so this becomes beta. And I can define beta beta. Now I need to define my Hamiltonian. S1 dot with S2. Okay. So I've already defined my Pauli operator sigma x, sigma y and sigma z. Sigma x you will observe is 0, half, half, 0. Sigma y is this, sigma z I've defined. I've already done that. So now I would like to define my Hamiltonian. So my exchange Hamiltonian is minus 2 times some constant j into S1x into S2x. So I put O cross tensor product AX with AX. This is S1x into S2x. Plus the y term, the y Pauli operators. Plus the z ones. So this is my exchange Hamiltonian. S1 dotted with S2 and it's symmetric. Okay. Now what I would like to do, I would like to compute the terms over there. So the top left term is going to be the exchange Hamiltonian. It's on the right, it's sandwiched by alpha alpha. So it acts on alpha alpha, and on the left it's sandwiched between alpha alpha. So I need a row vector here. So I put transpose AA here. And AA is real, alpha 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 beta, they are all real, so don't need to take a complex conjugate. So this will give me the first term, minus j by 2. I put this term in here. Okay, so I've calculated, what I've calculated, this term is alpha alpha hj alpha alpha. Okay, this is this inner product. I calculated this and put it here. Now I can calculate all the terms in the row. In the row, this alpha alpha, this bra alpha alpha remains unchanged, and I successfully put in a different input. 0, BA is 0, BB is 0. Sorry. So all other terms in here are 0. Okay. Now let's move on to the second row. In the second row, the bra is beta beta BB. Now successively put in all the values 0. BB is minus j by 2. So the second term is 0. All others will be 0. So the only non-zero term is this one. Second, this is this is also beta beta. This is, I have to do the same ordering here as here, alpha beta, beta alpha. Okay, so the same order in which I have the rows, I have the columns. This is alpha alpha, beta beta, alpha beta, beta alpha, alpha alpha, beta beta, alpha beta. So this is 0. This is minus j by 2. 0, 0. Now let's populate the third and the fourth row. So for the third row, my inner product is sandwiched between alpha beta. So I have AB here, and then I find out the successive terms. AA 0, BB 0, then I have AB j by 2 and BA minus j. So I have 0, 0, j by 2 and minus j. Let's do the last row. So for the last row I have BA. So I do it successively. AA 0, BB 0, AB minus j, BA j by 2, minus j and j by 2. Thank you, Mathematica, that's all of me for you. Okay. Now let's look at this Hamiltonian over here. Now can we diagonalize this Hamiltonian? We can break up this matrix into two blocks. One is the block that appears here, and one is a block that appears here. If I look at the first row, all elements are 0, and all elements are 0 here. So two eigenstates are evident. One eigenstate is alpha alpha. Alpha alpha is only connected to alpha alpha, it's not connected to any other state. So alpha alpha is an eigenstate of this exchange Hamiltonian with eigenvalues. So now I'm writing down the eigenstates for the exchange Hamiltonian. And here I'm writing the energies. The energy, since it's a diagonal block matrix, the energies are just the diagonal values. So this energy is minus j by 2. Likewise, beta is an eigenstate. The energy is once again minus j by 2. Notice that both of these are triplet states and they have the same energy. Now let's look at this block form. This block form is something we've already encountered. It has two diagonal elements that are equal and two off diagonal elements that are equal. Okay, so the eigenenergies so if you have such a form, the eigenstates are going to be superposition of alpha beta and beta alpha. So one eigenstate is going to be alpha beta plus beta alpha over under root 2. Okay, and the other eigenstate is going to be alpha beta minus beta alpha over 2. So with the help of this exchange Hamiltonian, we have naturally split up the spin basis states into two manifolds. One are the triplet states and the second is the singlet state. Now you notice that if you would like to find the eigenvalues of this block matrix, we've already found out that the eigenvalues are the sum and difference of the exchange of the diagonal and off diagonal terms. So you'll also find out using your linear algebra technique, you find out the eigenvalues. One is going to be the difference between this term and this term. It's going to be sum of this term and this term. So the sum is minus j by 2. So this triplet state has energy minus j by 2. Now this is going to be the difference. So j by 2 plus j, 3j by 2, right? Okay. And the separation between the singlet and the triplet manifolds is once again 2j. Okay, and you will also notice one thing. If J is negative, as it is in the hydrogen molecule, then the singlet is lower in energy and we recover the same kind of diagram that we've drawn over here. And remember one more thing, we've only looked at the exchange part. There are other energy terms that are coming from H naught and Hc as well. And those terms are independent of the spin. So on top of this, we'll have to add up 2E1 plus some Coulombic term to all of them. So these are the energy states, energy values for the singlet and the triplet state, and the Heisenberg Hamiltonian recovers the proper energies, and it recovers the proper singlet, triplet splitting even for the hydrogen molecule. So our test toy model, the Heisenberg model, works very well for the hydrogen molecule. It works perfectly for the hydrogen molecule. Now this value J has to be computed, and that comes from the direct ab initio methods. It's given by the overlap integral that I wrote in the beginning of that class. But this effective J, this is an effective exchange coupling constant. It effectively describes the singlet triplet splitting. That is the difference in energies between ferromagnetic ordering and antiferromagnetic ordering. And by the way, the Heisenberg model only gives you the ground state. It does not have the capacity to give you the excited states. Alright. So now what we're going to do in the next class, we're going to discuss the spin-orbit interaction, which is an extremely important interaction for real systems, because with the help of that we can describe paramagnetic ions, we can describe the differences between rare earth ions and transition metal ions, we can describe magnetocrystalline anisotropy, why do you have hard magnetic materials and soft magnetic materials, and the whole field of spintronics is heavily based upon the idea of the spin-orbit interaction. So we'll take a deep look at what the spin-orbit interaction is and what are the foundational principles derived from quantum mechanics for the spin-orbit interaction. So here what we've been doing so far is really applied quantum mechanics. We're applying quantum mechanics to some spin systems so that we can prepare ourselves to looking at real systems as they appear in the real world. Thank you.